To get the time it takes for a toilet paper roll to drop regularly, you just look at some kinematic equations and you rearrange them, and you get that the time it takes is the square root of 2h1 over g. But the time to unroll is a little bit different. That's the square root of 2h2 over a. A is not equal to g because it's being unrolled. And because of this, h1 over h2 is equal to g over a. And now the moment of inertia for the unraveling toilet paper roll is 1/2 m times r of the inside plus r of the inside squared plus r of the outside squared, and this is from parallel axis theorem. And because there's an unrolling part, we have to add a second moment of inertia, which gives us 1/2 m times r in squared plus 3 radius out squared. And now the net torque provided by the unrolling part is I alpha, and the angular acceleration is equal to the torque over the moment of inertia, which is mg r over 1/2 m r squared plus 3r squared. And this ends up being 2gr over r of the inside plus r of the inside squared plus 3r of the outside squared. And linear acceleration is equal to angular acceleration times radius. So when you multiply this by radius, you get 2gr squared over r squared plus 3r squared. And from before, h1 over h2 is equal to g over a. And so r squared plus 3r squared all over 2r squared, which equals radius of the inside squared over 2 times the radius of the outside squared plus 3/2, which is equal to h1 over h2. And with our measurements, we got that the ratio between h1 and h2 is 1.563, and our different heights were 3 feet and 4.69 feet. The 4.69 feet being for the one that was just simply dropped, and the 3 feet being for the one that was unraveled. And we'll demonstrate that now.